So we're wrapping up the third week of the trimester already. If you look at our weeks, we had a quiz on the very first week, quiz 1. And that, if you go to Delta Math, you could do the remediation on that if that quiz didn't go the way you planned. And this is not for your class specifically, but this is kind of all my classes together. Apparently I can't scroll. Let's see if yeah, you can kind of see it right here, but it's titled Remediation for Quiz 5.1. You can still do that, and you have up until April 4th to do that. So if your quiz didn't go the way that you want, all you do is complete that, and then once you're done, email me so I know to go back through, and I'll check it and then update your grade. And that's true for Quiz 5.2 as well. So let me show you. In week 2, we had the quiz 5.2. Then we also had the test on that Friday. So if you wanted to redo the quiz or even the test, if it didn't go your way, you can do the remediation as well. And all of those are currently linked in Schoology. I actually think I had you guys watch a video. I want to say it was on Friday. Oh, maybe not. Maybe it was on Thursday last week. Yeah, watch the video on how to do the quiz remediation. So I gave you a little message. I know that I wasn't present last week because I had to be gone, but I tried to communicate as best as possible. But I wanted to share with you my observations on the test that we had. So this test, those of you that did it actually did quite well. I did notice that when I checked your work, which by the way, thank you so much. I thought the work that you showed was wonderful because I could go through and check and see where errors occurred if they did. And to be honest, the largest error that I saw was multiplying or subtracting or dividing fractions. It had nothing to do with precalculus, meaning you guys understood the concepts at hand. It was just the fraction work that we needed to kind of review. So with that being the case, I was able to grade and give partial credit. And if you go through and check your Delta Math score, you might notice you got 0.5 points worth, or you might have got 0.75 worth of a point, or even 0.25. And that was based off of if there was an error, it was based off of the error, the severity of the error. If you got like 0.25 off, that means you just made a tiny mistake with some type of fraction. If you got 0.5 off, then that means that you made some type of like computational error where you maybe used the wrong, instead of doing a sine ratio, you maybe screwed up a sine ratio or a cosine ratio. If you got 0.25 wrong on something, or if you got 0.25 worth total, then that means you got like a larger area. You maybe used the complete wrong formula, or you showed your work, but it didn't go well. So what I did then is this test was out of 22 points. But if you look at your score in Delta Math, it was out of 11. So that 11 plus you got 1 point for each problem that you showed work on. So if you take the 11 points worth of Delta Math plus the 11 points for showing your work, that's where the 22 points came from. So just so you guys know, that's how that was scored. And if you're not happy with your score, you could do the Delta Math and do the remediation. Just please email me when you're done. And that way I know to go back and update the grade book for that.
Okay, I have a question.
Sure.
So if you get a question like wrong, but you still show your work for it, do you get a point for the work?
Yep. So like let's say that you did a question and it was Delta Math said you got 0 out of 1, so you got it wrong. What I did then was I went and I looked at your work, and if you showed your work, you automatically got 1 point. And then I looked for where was your error. Was your error something that was really tiny? Then that's where your Delta Math, I maybe changed it to like a 0.75. So if you got it completely wrong, but you showed your work, you still got 1 point. So if you didn't, and I actually had nobody so far didn't show any work. Like, what I mean is every single person showed work that did the test, which was super encouraging. The downfall is I still have, 15 people who didn't do the test yet. And that's the part that makes me a little nervous. So just so you guys are aware, you have until April 4th, which is Sunday at 11:59, to get all this unit work in, finish the test, get it all completed, and then we'll be good to really start this new unit, which we are starting today, but I'm hopefully you guys are seeing I'm giving you guys a little bit of extra time just because I was gone last week and I didn't give you all those daily reminders to get caught up. So, all right, we are shifting gears then, and we're going to start a new unit, which I think you guys are going to like. We're going to look at vectors, and those of you that have taken a physics class or maybe are currently in physics, vectors are used quite often. Vectors are a mathematical symbol that represents both magnitude and direction, which a lot of times is used with some type of force. And when we say force, what we mean by that is we mean it could be acceleration, it could be velocity, it could be position on how a vector is working. So I'll give you guys a second to, you don't have to technically write this first part down. Sorry. I'll give you guys a second just to kind of read through this. As soon as I see vector, right away I think of Despicable Me. And I think of that villain played by Jason something or other. But he always had this term, I'm applying for a villain loan. I go by vector. It's a mathematical term representing an arrow with both direction and magnitude. So a lot of times when I think of a vector, I think of wind, right? Think of how windy it was the other day. If you were to look at like a weather map that showed wind can blow in different directions at different times, but it also has a force behind it. And that's one case how vectors are used in the real world. So, that's not good. What's going on? Oh, okay, that's why. All right. So I'm going to give you guys a second to start writing this down, and I apologize for the small print down here. I'll let you know what that is in a second. But why don't we start with this part, copy it down. I will explain this. I just have to pick something up from the printer quick. When you think of a vector, think of an arrow, right? It's going to go in a direction, and it has a force behind it. There's a magnitude to it, which also can represent a length. A vector is an ordered pair of real numbers that represents a direct distance. So a lot of times if we're talking about a map, it would be like northeast or northwest or southeast, and it tells you the direction that it's going, but it also has a distance, right? It has a length to it. So when we talk about a vector, it has to have an initial point and a terminal point. And I just drew a quick picture here. Here's one where my initial point is kind of where it started, and then the terminal spot, I don't want to say is where it ends, but it's where you can think of it as ending. Terminal means an ending spot. However, it could be extended. But this distance and length is a representation of a vector. Okay, so graphically, that's what we're talking about. Now, it's an ordered pair. And that's the part that I want you to kind of look at is when we talk about the ordered pair, it's really like a position on a graph. So we'll show you the notation because it's not just a 0.43, but let's say that I had an initial point right here on the origin, on the spot 0, 0. Now when that happens, we have two components. We have a horizontal component and we have a vertical component. Well, hopefully this seems familiar. Right? If I wanted to get to this point, I always have my run, so moving left to right, and then I have my rise, which hopefully you're thinking, isn't that slope? Right? Rise over run is slope, and that's kind of where we're getting at. But there's a new notation that we're going to call the vector. So if I go horizontal and then vertical, that's the same thing as moving along this line, which is like the vector. So how do we represent that? Okay. Now, the important part here is when we say starting at the origin, that's our standard position. So it's when your initial point starts at 0, 0. And it will tell you, for the most part, that you're going to start at 0, 0. Okay? Now, the part that's kind of hard to read, and I thought it looked much better on my computer at home, is the horizontal component is always going to be the first part of your ordered pair. So that's how far you move left or right. And then the up and down portion is the vertical component. And notice how we have the different style of brackets. They're not the curved brackets. Now it's more like those chevrons or those arrows. That symbol is our mathematical symbol to represent vector. So that's how we're going to write this vector component. And we'll talk about how we can name them as well. So if I look at my example that I have up here, well, what did I do for my run? I ran 4 units, and I rose 3 units. So if I wanted to name this vector up above, it starts at the origin, and it ends at the point 4, 3. Well, its run is 4, and its rise is 3. So that is our symbol for vector AB. Now look at the symbol right here above that AB. Notice how it looks like an arrow, but it's kind of chopped off. That is our symbol for vector. Now, in geometry, you learned this one represented a ray, right? And where does a ray start? It has a starting point, and it has a ray technically goes on forever, right? So we would start at point A, and this would go through point B. But when you kind of cut that arrow off and turn it into a vector, that means that you're going to start at 0, 0, and then you're going to end by applying a run of 4 and a rise of 3. And there's the terminal spot. So initial and terminal. Okay. So this page is really just getting you guys to the notation. Honestly, it almost looks more confusing than it is. So I don't want you to overthink this page right here. Okay, so let's show you how this will be used. I don't think you need to write this at all. Let's just take a look at it, because once we know this, we're going to apply it to pretty much everything that we do. So I just want to cruise through this part. Vectors can go in any direction. They can start at anywhere and they can end in anywhere. So how would we represent this? Notice none of them start at the origin here. So none of these have that initial starting spot, which is completely fine. But if I'm going to name the vector, we have to be able to write it as a name and then its component form. So let's start with the red one here, AB. If I start at A and I go to B, there's my vector. What I need to do is I need to determine from the starting spot to the initial spot, what is my horizontal component? Oh, by the way, how do we name this? We would name it AB with the symbol. Now notice, it has to start at A, because that's the initial spot, and then it has to end at B, because that's the terminal spot. All right? And then how do we write the component form? We're going to use the vertical and the horizontal component. Well, the horizontal is how far do I move left to right? So 1, 2, 3, 4. And notice we are going in the left, so it's a negative direction. And then what's my horizontal component? Positive 2. Yep. We go up 1, 2. And isn't that just like creating a right triangle? Right? Remember when we did that in geometry and algebra 1 and all that? That's how we're going to do each one of these. So I'll do the blue one, and then I'll have you guys do the other two. How would I name the blue one? Well, it has to start at the initial side, and then we're going to end at the terminal side. So I would have to name this GH with that little vector symbol above. And then I can use the new notation. And then I just have to determine what is my vertical run or horizontal run first. That's always the first coordinate. So how far do I go over? 1, 2, 3, 4. So I go over 4 to the right. And then how far do I go down? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now notice I went down, so that's a negative 12. Okay? So why don't, it's kind of hard to read, but I want you to try, I'll make sure the arrows are more pronounced. There's the arrow on C, and then here's the arrow for D. Why don't you try the purple and green one quick? All right, let's take a look at these here. And for the purple one, we have to start at F and we go to D. So F has to come first and then D with a little symbol. The component form, what's my horizontal run first? So I'll start at F and go over 1, 2, 3, 4, 5, 6. With 6 to the right, so it's a positive 6. And then I'm going to go up 1, 2, 3, 4. So positive 6, positive 4. Nothing crazy. For the green one, we are starting at E and ending at, what is G? That's C, that's C, I think. Ending at C. And in this case, if I start at E, I don't move left or right, which means my horizontal component is 0, and then the vertical, how far up? 1, 2, 3, 4, 5, 6. And it's the positive direction, so positive 6. 0, 6. Now, there is one other way that we can name a component or a vector. That might be this. If you ever see a vector, like let's say I go from G to H, and if you ever see a lowercase letter just written right next to it, that could be vector t in this case. Okay, and I just made up t. I don't know why I chose that. Or if I have this, let's say that I've got lowercase g, the purple one, we would name as vector g. It's kind of like geometry, right? Everything has to have a symbol and has to have ways to name it, and sometimes we can name it in different forms. And then also I want to quick point out, what if I called the vector CE? Right? That changes things, doesn't it? It changes where we start. So in this case, if I start at C and I go the other direction, its component form is going to be different. We're still going to move over 0, but my vertical component goes the other direction. So it's going down because I would start at C and count down, so it would be a negative. So it's important to understand that the way we write it has the effect on how the horizontal and vertical component work. All right. What I would like you guys to do is determine the components of the vector if I give you the starting spot, the initial spot, and the terminal spot. Now, if you'd like, you can draw a quick sketch. Or, can you figure this out without a sketch? But I want you to try this problem really quick. So when you have a problem like this on Delta Math, you have two options. You could draw the graph and go over 1, up 1, 2, 3. And there's my initial point. And then the terminal point, go over 7. 1, 2, 3, 4, 5, 6. So let's 1, 2, 3, 4, 5, 6, 7. Up 1, 2, 3, 4, 5, 6. And then you know that your vector is going to start at the blue. And there, notice how they call it vector v. So I would use a lowercase v there. And then you have your component. How far do I go to the right? 1, 2, 3, 4, 5, 6. I go 6, positive 6 units to the right, and up 1, 2, 3. And then your component form would be 6 to the right and 3 vertical. Okay? Now, is there a faster way to do this? Right? And there's a rule that I don't think you need to really use the rule. But what is this horizontal component? Well, it's the difference from where you start to your end in the x values. Right? So how did we get the 6? Well, if I took 1, and we should always do the biggest number first, right? Because where did I end? We always start with the 7, and we're going to subtract the 1. So 7 minus 1, that's how we got 6. And that's my horizontal component. And then how do I get the vertical? Take the y value of 6 minus 3. And that will give you your vertical component. Right? So all it is it's the difference of your y values and the difference of your x's. Now, there's so do we really need a graph? No, because we can do this using that tip to tail method. And this is what you can kind of think of. So this is more mathematical, but let's look at it. If I have an initial point, and then I have a terminal point. Well, how do we find the horizontal component? You take the x's and you subtract them, but notice it's the tip to the tail, basically the head minus the tail, if you want to think of it that way. But you're taking the terminal point, minusing the initial point for your x's, and that gives you your first component. And then to get the second part, take your y2 minus your y1, and that's how you get your second part. And that's exactly what we did here. So without a graph, you can get this much faster. It's just subtraction. You might even think of, isn't this just slope? show you maybe a better way to write this or think of it. That's how I think of it. What's your horizontal component? It's just this x value minus this x value, and it tells you the difference. And what's your vertical? This one minus this one. The reason why it's called the tip to tail or head to tail is if your vector is headed in a certain direction, wherever it's headed is always your y2 values, x2, y2, and then wherever it started is the tail. So think of it as like, here's where it started and it keeps on going. I don't know. If that helps you, cool. If not, I just think of it more as this is very similar to slope. All right, so I'm going to have you guys try some, and this is where I thought it was bigger, but this is very similar to some of your delta math problems. So your job is to have the initial and terminal point, find the components of vector v, and I just have two problems here. So go ahead and try those quick. Do this all in your head if you want. So the important thing is if you consider this your initial point, that's always x1, y1. Because that's where we start. And then where we're headed towards is x2, y2. And then your horizontal component is, in this case, the 8 minus 6, so I get 2. And then the y components is y2 minus y1, so negative 6 minus negative 5, then that turns into addition. So vector v would have the component 2, negative 1. And then basically same thing here. Make sure subtraction of a negative ends up being addition, so you get 1, 0 for that vector. Pretty quick. I think you guys are going to cruise through the delta math tonight. So that's basically how we write what's called components of a vector. And again, we could graph these if we want to, because they do have a visual representation. But what about other operations? I don't know if you need to write this. I think the next example will be fine. But what if I have two different vectors? And how do I do operations? And now think of when we say operations, that's adding, subtracting, multiplying. We're not going to get into division at all, but we're going to look at, well, how do I add or subtract? Vector addition is, what if I have vector u plus vector v? Well, picture this as like a trip. If I take a trip to this point right here, I have to go a certain horizontal and vertical distance. And then if I want to go to another destination, I'm going to follow a different road or take a different vector, and it'll get me there. But what if my goal was just to get to the second destination and skip the first one? Couldn't I just go on the red vector? And the answer is yes. So how do we add vectors? Well, since we're moving the same horizontal distance from left to right to get to this point, and then from here to here, isn't that the same as just moving all the horizontal distance at once, and then moving all the vertical distance at once? Okay. Now the same is true for subtraction if I want to take away two vectors, and we'll look at that. But notice what they did. If I want to add vector u plus vector v, all I do is take the horizontal components and I add them together, and then I take the vertical components and I add them together. So if I know what v and u are, to get the total horizontal distance for the red one, I would just add those together. If I know the vertical components of each, I would add the vertical components, and notice it gets me to the exact same spot. So it's just building off of one another. So again, this is something that, do we really need to do a graph for this? This would be something that you would do in Delta Math. So I'm going to show you this visually. I don't want you to write this part down, but then when we check our answers, I'm going to have you guys check it using the idea of adding them together. So let me just show you how this would work. So if this was a Delta Math problem, it says you have vectors u and v, and you can tell which one is which. If I go over 7 down 3, here's vector u. And then if I go over -5 down 5, here's vector v. And it says find the sum. So I got to add those two together. Well, graphically, what are we going to do? We're going to take one of them and drag to the other one. So what if I take this one and I say, okay, let's start with v first. So I'm going to travel down v, and then I'm at this point right here. I'm at this ending spot. And what if I grab this line now and I apply it over here? Where am I going to end? I'm going to end at this point right here. Right? Now, where would that be from the origin? Well, how far over do I go? 1, 2, and then down 7. So if I drew this spot in there, I would be at the vector, and maybe I name it another vector. Let's call this w. So my answer, vector w, would be over to the right, down 8. Now, is that the only way to do it? Well, what if I decided to leave u, and I decided to apply u first, which got me to this point right here. It got me to this point right here, and then I apply v. Notice, I end up in the exact same location. So it does not matter which vector you move. All right? Either way, if you apply one and then the other, it'll get you in the same spot, which kind of says all we're going to do is we're going to add the vertical components together and the horizontal components. So let's start with the vertical. If I take u plus v, let's do vector u plus v. So I'll do the u and v in red for the horizontal components, and then in blue, we'll take -3 plus -5. And when I add those together, I get +2 down 8. And notice, doing it numerically is the same thing as we got doing it graphically. All right, so you should be comfortable. If there's a graph provided, you can move those and get them in the spot that you need to. Okay? Or you can check or do it completely without a graph just by adding the horizontal and vertical components together. So that's addition. Subtraction works the same way, but we would be taking it away. But what about multiplication? Okay? And again, you don't have to write this one, but let's think of that. What if I have a vector that is this length right here, the size of u, and I tell you that I want you to do 2 times the vector u. Well, what does that mean? That means I'm going to take this value, I have to do it on my computer, and I'm going to bring it over here once. So there's u, right? Those are the same length. Then I'm going to clone it and do it again. And now the length of 2u is just double the value that we ended for 2u. Well, if I have 2 times u, I can just take this multiplier and times it by both the vertical and the horizontal component. So instead of going over a certain value and up, I'm going over twice that value and up twice as high. That's how the multiplier works. Okay, now what if I times it by a negative? So what if I took this and times it by a negative? The only thing that's going to happen is the arrow is going to switch. Okay, so let's see if I can apply this direction. In green would be negative u. So what if I times that by 2? Well, then I would have negative u in one direction and then negative u again. Notice it's still the same length as the positive value. The only difference is the direction has changed. So when you times by a negative, that changes the direction that the vector is headed. Okay, or let's look at this last one. If my original blue one was u, and I wanted to do 1/2 of it, notice, if I was to cut this in half, that's the size of half u. Okay? So, things to think of. What happens when we multiply by a number greater than 1? So what happened to my problem when I multiplied it by 2? It grew in length, but it headed in the same direction. So I think that's just important. The vector grew in length, headed in the same direction. So nothing crazy. You can visually see that the blue ones are still twice as long and it's headed in the same direction. Now I might, instead of the word length, I might say magnitude, because magnitude refers to the length that a vector is going. This one's important. What happens when I multiply by a positive number between 0 and 1? Well, think of what kind of numbers are between 0 and 1. Those are numbers like 1/2 or 2/3. You're taking a portion of the whole, so it's not going to be as big as the whole, it's going to be smaller than the original. So this will shrink in length, or actually, I might throw that word magnitude, if I can spell it. Is there an N there? Is that right? That doesn't look right. Is it? You guys haven't seen it too much, but I'm horrible at spelling. I am the first one to admit that. It's going to shrink in magnitude or length, but we are going to head in the same direction. So then what happens when we multiply by a negative number? Well, if it's a negative greater than 1, we're going to grow in length, but then we'll go in the opposite direction. Or if it's a number between 0 and 1, we're going to shrink, but then we head in the opposite direction. So and that's just things to think of when you're multiplying numbers together. You should already know. Yes, sir.
Whenever you talk about that first bullet point, you underline same instead of opposite.
Oh, right here?
Yeah.
Yeah, so when it was multiplied by a positive number, it headed in the same direction. When it's multiplied by a negative, it's not same, now it's opposite. So it's just flipped around. It's kind of like we had here, going in the opposite direction. So I was just showing you that it's the opposite of that one.
You could usually use the opposite of what you want to find.
I guess I was trying to show you that this was the same when it was positive, and then I see what you're saying. Yeah. All right, so these are things just to keep in mind, and I'm a visual learner, so when I'm doing the work, I kind of think of it visually of where would it be headed, what does it look like, and what's happening to it. I'm more, I also think about the answer, but I like to think of that as well. So let's say we have this. Here is my given information. You know what U is, you know what V is. We want to subtract U minus V. Then we want to do negative 3/2 times U, and then we want to apply multiplication with addition, or you can kind of think of that as subtraction. So I'm going to give you a second to write these down. Have everything. So you can show as little work as you need, or you can show a lot of work here. I'm going to just show the work that I think is interesting. But what if I wrote it as subtracting the vectors like this? Right? There's U minus V. I have to be very careful because I have to connect them with the fact that I'm only subtracting the horizontal components, and then I'm only subtracting the vertical components. So when we write this, my answer is still going to be a vector. It's going to be in the component form, but I'm going to have when I subtract them, it kind of doesn't matter, but we want the 4 minus negative 1, and then we want the 7 minus the 3.
Okay, so why are they switched?
So if I go back, let me go back to this slide. Where's the slide that we had? Here we go. So, why did I flip it? That wasn't it. I don't know why I flipped that. I think I got it flipped around. Yeah, I shouldn't have flipped it. I was thinking of starting from 0, finding the differences from the horizontal vertical. So, nope, just subtract. Same way you did. And then there's your new vector. It is important to understand that that answer is a vector. It's not an ordered pair, it's not a point, but it's the location. And we could graph these to see how that works, which might be interesting. We just don't have a ton of time today. So what about multiplying? Well, we're going to multiply negative 3/2 by U, which now it's like the distributive property. You're going to literally multiply each one of those vectors. So then negative 3/2 times 1 is a positive 3/2. And negative 3/2 times 3, you can remember that is the same as 3 over 1. So when I multiply fractions, we multiply the top by the top and the bottom by the bottom. Numerator times numerator, denominator times denominator. Yes, sir.
So you want that in fraction form?
It doesn't matter unless the directions say specifically. So either way that it's written, this still tells us the horizontal movement, and then this still tells us the vertical component. So you can still read it in decimal or fraction. If the directions say write in fraction form, then we're looking for this one. So just make sure you read them carefully. Part C is just putting it all together. But you have to follow order of operations. Remember PEMDAS? Please excuse my dear Aunt Sally. You have to do parentheses and then multiply and divide. So in this case, we have to do the multiplier of 2 first and the multiplier of -1, and then we can add the components together. So what I would do is write out the multiplier first. And apply both of those the same way we did part B, and then do the addition. So when you do your multiplier of 2, that gives you new products for your horizontal, and same thing with the -1. And then it also gives you the new pieces for the vertical components, and then we can add those two together. -2 plus -4. Some students like to do this. I don't think you need to, but technically that's what we're doing. Some textbooks will actually have you write it this way, where it shows the horizontal pieces being put together, it shows the vertical components being put together, but you can do that in your head and get the final answer. And there's your new vector. That is W plus -1b. So we talked about adding, subtracting, and multiplying vectors, and we talked about what that looks like graphically. Okay. So our homework tonight is just the basics. It's pretty quick. Those of you coming back in the afternoon, I'm guessing you're going to finish in 10 minutes. So that's all we got. A reminder, I'll just put this up here, is all Chapter 5 late work is due on Sunday, okay, and some of us need to still do that test that's out there. So please make sure you plan accordingly. Tomorrow we don't have any classes or anything extra going on.